Hi everyone, thanks for watching. I'm Michela Sestu from University of Cagliari and NFN Cagliari, and today I'm going to discuss the results we obtained by analyzing neutrino data from direct detection dark matter experiments. This is the outline of my talk. I will first describe low-energy neutrino-elastic interactions, and in particular the coherent elastic neutrino-nucleus scattering, also known as CENNS, and the neutrino-electron scattering, known as NUS. Then I will prove that the Sun is a powerful neutrino source of all flavors, and I will explain how these neutrino signals can be detected at direct detection dark matter detectors. The main part of the talk will focus on the results we obtain by analyzing data from like XENONnT and PandaX-4T and LUX-ZEPLIN collaborations. So first of all, let me give you an introduction on neutrino interactions at low energies. So we are specifically talking about neutrino energies below 100 MeV. In this energy range, we can have interactions of neutrinos with electrons. In this case, we only have an elastic interaction, which is known as NUS, as I said before, but we can also have neutrino interactions with nuclei. In this case, we can have both an elastic and an inelastic interaction, but for the purpose of my talk, I will only consider elastic interactions. So the elastic interactions with nuclei, which is CENNS, and the elastic interactions with electrons, which is NUS. Let's start with CENNS, which stands for coherent elastic neutrino nucleus scattering, and as you can see from the diagram here on the right, it is a neutral current process because we have a neutrino which scatters over nucleus, and then the process is mediated by a Z0 boson. But the particular feature of this process is that the wavelength associated with the Z0 boson is bigger than the size of the nucleus, which means that we have a coherent scattering, so that the nucleus recoils as a whole. And what we can do is that we can measure the very tiny nuclear recoil it produces, which is below 10 keV. So of course this is experimentally challenging, but measuring CENNS also represents an opportunity, and I will explain why in a minute. So let's give a look at the cross-section. This cross-section depends on different quantities, for example neutrino energy and the nuclear recoil energy T, but we also have this quantity, which is the weak charge of the nucleus, which depends on the two form factors, the neutron and proton form factors, which account for the distribution of protons and neutrons inside of the nucleus, and it also depends on these neutrino couplings with protons and neutrons. I report here some values which include the radiative corrections, and as you can see, the neutrino coupling with neutrons is bigger than the neutrino couplings with protons, meaning that the cross-section scales as the number of neutrons squared. And this makes the CENNS cross-section enhanced compared to those of other neutrino-nucleus interactions at the same energies. That's why it's an opportunity to study CENNS. Now let's move to NUS, which stands for neutrino electron scattering. As I said, it is an electron scattering, and we consider atomic electrons. So the cross-section is the following. We have that it depends again on the energy of the neutrino and on the electron recoil energy. Again, there are these couplings with the electron, and we also need to have this quantity, ZF, which accounts for the number of electrons that can be actually ionized for a given energy deposit T. If we consider a free electron, this quantity is not necessary anymore. To conclude, I want to show a comparison between some CENNS cross-section, which you can see here represented by the blue curves, which are different because they are for different nuclei. And for example, other cross-sections at the same energy. You can see, for example, here the neutrino electron cross-section represented by the red dotted line, and you can see that the CENNS cross-section is larger. So that's why we are particularly interested in CENNS. Okay, so as I said before, one of the sources of neutrinos at low energies is the Sun, and the Sun produces neutrinos of all flavors at very low energies, so for energies below 20 MeV, and this is important because these are suitable energies for the processes we want to study, so for CENNS and NUS. Solar neutrinos are produced inside of the Sun through two thermonuclear reactions, which are the PP chain and the xenon cycle. And as you can see from the diagram here, there are many steps in these reactions, and in particular I represented by the color boxes the steps in which electron neutrinos are produced. So if you look at the plot here on the right, we have the black curve, which represents the total solar neutrino flux, and some colored lines, which represent the components corresponding to the colored box on the left of this total solar neutrino flux. For example, the main contribution for the CENNS interaction comes from mainly from boron 8, but there's also an EP component of the flux which contributes to CENNS, and the PP component of the total solar neutrino flux contributes mainly to nu-S. Now, what we can do is that we can detect solar neutrinos through direct detection dark matter experiments, which of course are primarily meant to search for signals from WIMPs, a class of dark matter candidates, but can also detect neutrinos. And let's see why. So these experiments use dual phase time projection chambers, or TPCs, which are filled with some noble gases such as argon, or in our case xenon. What happens when an incoming particle hits nuclei or electrons inside of the TPC? So we have a primary scintillation signal S1, and the electrons that are produced in this first interaction are then drifted using an electric field through the gaseous part of the TPC, and here a second ionization signal is produced. In this way, we are able to trace the particles. So when we want to look for dark matter, we expect WIMPs to produce some nuclear recoil signals. And so CENNS, which also produce nuclear recoil signals, and nu-S, which produce electron recoil signals, represent irreducible backgrounds for these experiments. And this, of course, represents a problem if we want to look for dark matter, but it's an incredible opportunity if we want to study neutrinos. And that's what we did. So we considered 5 datasets coming from 3 xenon-based dark matter experiments, which are XENONNt, PandaX-4T, and LUX-ZEPLIN. And in particular, the CENNS data that we consider are the first evidence of CENNS from solar neutrinos. And so from now on, I will explain the results we obtained in our work. Okay, this is how we did our data analysis. On the left, we have an histogram in which we reported one of the 5 datasets we used. In particular, this is CENNS data from PandaX-4T. We have that the colored histograms are the fitted background and signal CENNS events reported by the collaboration, and our prediction is represented by this red line. We want to compare the theoretical number of predicted events to the experimental data. So what we do is we use a Gaussian least squares function in the case of CENNS, and we use a Poissonian one for nu-S. So by varying theoretical parameters, we change our prediction, and this key-to-square comparison shows which values best describe the data. In this way, we are able to perform some standard model tests and also to explore beyond the standard model scenarios. And so now I will present some of our results regarding the standard model tests and the beyond the standard model tests. The first standard model test we performed is the measurement of the normalization of neutrino fluxes. In this case, we used only CENNS data coming from XENONNt and PandaX collaborations. And as I said before, the main contribution to CENNS comes from boron 8 neutrinos. So in the case of boron 8, we have measured the flux, and our result is in agreement with the solar model. In the case of the F flux, since it is a subdominant component of the flux, we were only able to put an upper limit, which has to be compared to the best limit from SNO. there's only one magnitude order of difference between the two. Another standard model test we performed is the measurement of the weak mixing angle. As you know, it describes the electroweak coupling, and it is a fundamental test of standard model because it is well known by theory, and any deviation from this prediction can indicate new physics. We also know that the weak mixing angle varies with the energy scale, and we are interested in particular in the low energy part of this plot. So I only consider low energies, and we are able to measure it because the weak mixing angle enters the cross sections of CENNS and NUS interactions uh, in this formula. So it enters the vector couplings. On the left, I reported our results compared to the results obtained from other experiments. In particular, this is the results we obtained from electron recoil data, and it is the lowest energy measurement of the weak mixing angle. And this one are the results which we obtained from nuclear recoil data. Of course, we have large uncertainties, but this is also the first measurement from solar neutrino data with dark matter detectors, so precision is expected to improve in the future. Another standard model test we performed is the measurement of the neutrino charge radius. So we know that neutrinos are neutral in the standard model, but if we consider radiative corrections to the vector couplings, as you can see from the formulas here, we can obtain a neutrino charge radius, which depends on the flavor. So we have an electron, a muon, and a tau charge radius. Since the Sun is the only source at low energies that provide us tau neutrinos, we decided to report here only the global fit considering the tau charge radius. And so on the left, we have reported the results for the 5 datasets, and the green curve represents the combined fit from all datasets. And our result is from the global fit is in this green box, and this is the most stringent constraint that we obtain from neutrino scattering experiments. Now let's move to some beyond the standard model scenarios, and in particular, in some of these scenarios, neutrinos can acquire a magnetic moment. In the simplest extension of the standard model, this magnetic moment is proportional to the neutrino mass, as you can see from the relation here, and it should be of the order of 10 to the minus 19, while this is to be compared with the best experimental upper limit, which is of the order of 10 to the minus 12. So we still have 7 orders of magnitude difference between theory and experiments. When we consider a neutrino magnetic moment, we simply have to add a contribution to the CENNS and NUS cross sections, as you can see here, and in particular, this contribution strongly depends on recoil energy. So this NUS cross section is particularly enhanced when considering this scenario, and that's why we only use electron recoil data to make this analysis. Another electromagnetic property we can consider is that neutrinos can acquire a small electric charge known as millicharge because it is very tiny, and the strongest constraint in this case comes from neutrality of matter, which puts an upper limit of 10 to the minus 21 in unity of the electric charge, and in this case the contribution, if we consider a neutrino electric charge, is taken into account by adding a correction to the vector couplings, both in the case of CENNS and NUS. And again, we have that these contributions strongly depend on recoil energy. So again, the NUS cross section is particularly enhanced, and that's why also in this case we consider only electron recoil data to perform the analysis. So these are the results we obtained for these two neutrino electromagnetic properties. We have these here the neutrino magnetic moment and here the neutrino millicharge as a function of the neutrino type. In our case, we consider solar neutrinos, so these are our results, and also these are our results. which we compare with results from other experiments. And as you can see from the plot, these are among the strongest laboratory constraints that we have. The last scenarios I want to explore, considering beyond the standard model physics, is a scenario in which we add some light mediators. In particular, we consider this L mu minus L tau light mediator, in which we have a new vector mediator Z prime, which is similar to the Z boson but lighter. And as you can see from the diagram here, the new boson couples directly only with mu and tau flavors. Again, the contribution, if we consider this light mediator scenario, is taken into account by adding this quantity to the vector couplings. And here we have that in this contribution we have the Z prime coupling constant and the new Z prime mass. So we put some constraints on these quantities, as you can see from the plot here on the left, by using our 5 datasets, but we also made a comparison with other constraints obtained from other experiments, and we also added the latest measurement of the G-2. So to conclude, direct detection dark matter experiments provide a powerful tool to probe low-energy neutrino interactions with nuclei and atomic electrons, and these CENNS and NUS data allowed us to perform some tests of the standard model and to explore some scenarios beyond the standard model. The main results we obtained include that we put some upper limit on the F-flux. We also provided the lowest energy determination of the weak mixing angle, and we obtained among the strongest laboratory constraints on electromagnetic properties, so on the neutrino magnetic moment and on the neutrino millicharge. Now let's talk about some future outlooks. Of course, as I said previously, the current precision is not so high, but it is expected to improve if we consider upcoming dark matter data. And we can also include the inelastic channels to have a more comprehensive picture in the future. That's it, and thank you for your attention.